Welcome to this week's second lecture. In the last lecture, we have seen the general decomposition of Cn into some invariant subspaces, which are the null spaces of A minus lambda I to the identity to the power mi. And we have also seen about some facts about the structures of these individual null spaces. So let me first repeat what we have seen. So if we have a matrix A, which is in Cn by n, then we are going to have its characteristic polynomial in the following structure: S minus lambda 1 R1, S minus lambda 2 R2, going until S minus lambda k Rk. Then here, the important thing that we know is that the summation of those powers, those multiplicities in the characteristic polynomial should be n. R1 plus R2 going until Rk is n. And the minimal polynomial of this matrix is going to have the following structure: S minus lambda 1 m1, lambda 2 m2, going until S minus lambda k mk. And we know that each of these mi's are between 1 and Ri. Okay? So then we have defined the following matrices. So I have defined sigma I as A minus lambda I identity. Okay, this is our definition. So that is what sigma I is. Then we can actually write Cn into a direct sum decomposition of the null space of powers of those matrices. Okay, so I have null space of sigma 1 to the power m1, null space of sigma 2 to the power m2, going until null space of sigma k to the power mk. Okay? We talked about the dimension of these null spaces, and we know that their dimensions are R1, R2, going until Rk. These are showing the dimensions. Okay? And then these are the invariant subspaces, and we know that if we use this decomposition, if we find basis vectors for each of these subspaces, and if we fill a P matrix, basis change matrix, with their basis vectors, and then if we make a basis change, we can obtain, if we choose those basis sets in a specific way, we can obtain the Jordan canonical form of the matrix as the simple representation of A. Okay? And here we have seen then the structure of these null spaces. We have seen that these null spaces, null space of sigma I, they're actually always strictly growing, okay, for some power increases. Okay, so I would have this. Maybe I shouldn't write the third one here. So let me just say that this is going to continue until null space of sigma I to the power mi. Okay? This strict growth, this is a proper subset sign, and it means a strict growth here as the power of the matrix increases. And afterwards, if I increase the power any more over mi, then this increase no longer continues, and we have exactly the same null space then, and this equality would continue forever. Okay, and we know that this largest null space that we obtain in this manner, which is inside this decomposition, is obtained with the dimension Ri. Okay, so the largest null space is obtained at the first obtained at the power mi, the minimal polynomial power of the same eigenvalue lambda I, and the dimension of the largest null space becomes the power or the multiplicity in the characteristic polynomial of the same eigenvalue. Okay, so here if I try to draw a pictorial representation of these null spaces, this is the null space of sigma I. Actually, this is the eigenspace. Okay, we know that null space of this matrix is the eigenspace of the matrix. This is where eigenvectors live. Okay, so if the dimension of that null space gives us the number of eigenvectors corresponding to the eigenvalue lambda I. Okay? Dimension of that eigenspace is the number of linearly independent eigenvectors of the eigenvalue lambda I. So this is the eigenspace. As I increase the power, the null space gets strictly larger, sigma I square. Okay? And this growth continues. This is null space of sigma I to the mi minus 1. And I have one more growth at null space of sigma I to the mi. And this is the largest null space that I can obtain for this matrix. And the dimension of this largest ellipse here is Ri. Okay, it is the largest subspace that I obtain. And if I increase the power further, I would obtain exactly the same ellipsoid. So these are the pictorial representation of these null space. And the eigenspace is the innermost space here. And all of the others are adding some disks into this eigenspace. Okay? So when we try to find the P matrix that would put the matrix into its Jordan canonical form, I will be drawing this type of figures over and over. You will get bored of me. Okay? So here I just wanted to show you a glimpse of what we are going to draw. So in this lecture, based on these facts, we are going to find how to find out the Jordan canonical form of a matrix. Okay? So we know that here we can choose P matrix. This P matrix can be formed out of the basis vectors of these subspaces. And these subspaces are invariant under A. And we know that if we choose the P matrix out of the basis vectors of these null spaces, then we can bring the simple representation of the linear transformation A into a block diagonal form. And each of those blocks would have size Ri, the dimension of these spaces. And furthermore, we have seen that if I choose my basis vectors very, very carefully in a specific way, then I can bring those blocks, Ri by Ri blocks, into a very, very specific structure, where I have eigenvalues on the main diagonal corresponding to the block, and one above the main diagonal I have zeros or ones, and everywhere else the block would be equal to 0. That matrix is called the Jordan canonical form of A, and it is shown with the letter J. All right? And here, of course, this is P inverse AP. And here, in this course, in the coming lectures, we are going to ask what is J for a specific A matrix, and how I can find a P matrix that would satisfy this relationship between A and J. Okay? So these are going to be the two questions that we are going to be asking. What is J and what is P? In this lecture, we are going to be asking the first question, what is J, and how can I find the Jordan canonical form corresponding to a matrix A? Okay? In order to be able to understand this topic, we are first going to concentrate on a single matrix in Jordan canonical form. Okay? So this matrix is going to be a 10 by 10 matrix. So this A is going to be composed of, I would have this type of matrices, 2, 2, 1, 0. And I would have 2, 2. And I would have 3 eigenvalues at 3. Okay? So this is my 10 by 10 matrix. And this matrix is in Jordan canonical form. Okay? And now we are going to be asking some questions about this matrix. So the questions are going to be, what is D of S? Sorry. What is D of S? What is M of S? And I'm going to be asking the following question. What is the dimension of null space of A minus 3 identity to the power L? Okay? For any L, I will try to find these dimensions. Sorry, this is going to be the first eigenvalue. Then I will ask the other question about the second eigenvalue. A minus 3 identity to the power L. There's a question mark. Okay? So we will be asking these questions and answering them one by one. All right? In order to be able to understand the answers of these questions, we are first going to be looking at a single Jordan block here. So you see that this matrix is block diagonal, and I can actually have a 7 by 7 block here with the eigenvalue 2. That is A1 bar, and I have a 3 by 3 block for the eigenvalue 3. Okay, and that is A2 bar. And I know that each AI bar is composed of some individual Jordan blocks. I have a 3 by 3 Jordan block, 2 by 2 Jordan block, and 2 1 by 1 Jordan blocks here. And I have 1 2 by 2 Jordan block and 1 1 by 1 Jordan block here. All right? So in order to be able to understand the answers of these questions, I'm going to concentrate first only a single Jordan block. Okay? Let me say that A1 is this matrix 2 2 2 1 1, a single Jordan block with size 3 by 3. By the way, this A is in Jordan canonical form. Okay? A is in Jordan canonical form. JCF is going to mean Jordan canonical form. Okay? So I have a single A1 matrix this is a Jordan block. Each one of these blocks are Jordan blocks. 1 by 1 Jordan block, 2 by 2, 3 by 3, 2 by 2, and 1 by 1 Jordan block. Okay? Now, what is the characteristic polynomial of this single Jordan block? The characteristic, this is an upper triangular matrix, therefore all of the eigenvalues are on the main diagonal. Okay? So the D1 of S, the characteristic polynomial is going to be S minus 2 cube. Okay? And I don't know about the minimal polynomial now. But let me look at, so I have only a single eigenvalue 2, and now I'm going to look at A1 minus 2 identity, this matrix. Okay? Just like this one here. A1 minus 2 identity is 0 0 0, 1 2, sorry, 1 0 0, and 0 1 0. I have this type of matrix, A1 minus 2 identity. Now I'm going to be looking at the dimension of the null space of this matrix. So this is going to be like sigma 1. So dimension of A1 minus 2 identity, null space of the dimension of the null space. Okay? So you see that as soon as I subtract 2 from the main diagonal here, I get a 0 column here. This 0 column is going to be important for us. So what is the rank of this matrix? I have a 3 by 3 matrix, and what is the rank? Rank is the number of linearly independent columns here, and I see that I have 2 linearly independent columns, these two. All right? And what about the dimension of the range space? Dimension of the range space is going to be, dimension of the null space. Dimension of the null space is going to be given by the rank nullity theorem. Dimension of the range space is 2, rank is 2, and number of columns is 3. By the rank nullity theorem, dimension of the null space of this matrix should be 1. Okay? So this dimension is 1 here. Okay? Now let me look at the square of this matrix, A1 minus 2 identity square. When I take the square of this matrix, I multiply this matrix with itself. I get this matrix then. So you see that these ones here in this matrix, they traveled 1 row up. Like this, okay? They were here, and then they came here only. The number has decreased, and they came here. All right? What about the dimension of null space of this matrix? A1 minus 2 identity square. Okay? In this case, this matrix has only a single non-zero column, which means that its rank is 1, and therefore the null space dimension should be 2. So what happened here? So when I actually looked at only a single Jordan block, when I subtract the eigenvalues, I get zeros here. Okay, every 0 on the main diagonal. And as soon as that, I get 1 0 column here, which contributed to the null space dimension, which is 1 here. And as soon as I took the square of the matrix, these ones traveled here onto this corner, and the null space dimension has increased by 1. Okay, because of this additional 0 column here. Okay. This additional 0 column contributed to the null space dimension, which increased by 1. All right? Now let me take the cubic power. A1 minus 2 identity cube. In that case, I would multiply these two matrices, and it would be here. Okay? So I get a 0 matrix in this case. What is the dimension of the null space of the 0 matrix? What is the rank of this matrix? Number of linearly independent columns is 0. There are no non-zero columns here. Therefore, the rank of the matrix is 0. What about the null space dimension? For any vector in C3, if I multiply this that vector with this matrix, it is going to be 0. Therefore, all vectors in C3 are in the null space. That means dimension of null space A1 minus 2 identity cube is 3. Okay? And actually, this is the largest dimension that I can get from this matrix. What was the largest dimension? It was Ri. And I have here, this is my characteristic polynomial, and R1 is equal to 3 here. So you see that this dimension, this null space dimension, can be at most 3. And the first power that I reach that dimension is again 3. Okay? So that means that the minimal polynomial of this matrix is going to be S minus 2 cube. And 1 is going to be 3, and R1 is because R1 is 3 here. And because we reached the dimension R1 at the power 3 here, this minimal polynomial power should be, maybe I shouldn't write it M1 here, but this is going to be 3 as well. Okay? So now what I'm going to do? I'm going to take the 4th power. Do you think the null space dimension is going to increase? A1 minus 2 identity to the power 4. I will multiply the 0 matrix with the matrix itself. Obviously, the result is going to be 0. Okay? But we know that once we reach the dimension R1, we won't be able to increase the dimension of the null space. Okay? And dimension of null space of A1 minus 2 identity to the 4 is going to be 3, and this is going to continue for any higher powers. All right? So now what happened when we went from power 2 to power 3? In that case, this 1, which came into this corner, disappeared altogether. Okay? No ones remain in the matrix anymore. And we see that here we get an additional 0 column here, which contributed into the increase of the null space dimension from 2 to 3. Now I have 3 0 columns, which means that dimension of the null space would be 3. Okay? So you see what happens to a Jordan block when I subtract the eigenvalues from its main diagonal and when I take its powers. First, I would have 1 0 column, and then when I take the square, these ones are going to travel 1 row up, 1 diagonal up, and they will come to this corner. And you see that in that case, the number of 0 columns increases and the null space dimension increases. Okay? And when I take the further power of it, then this 1 disappears altogether. What is this power? This power is the size of the Jordan block. Okay? I have a 3 by 3 Jordan block. When we reach the power 3, we are going to get the largest null space. And if we increase the power above the size of the Jordan block, no additional contribution to the null space dimension is going to come. Okay? So that is how a single Jordan block behaves in this case. Okay? So we have this interesting behavior. So here there are things that you should keep in mind. So when I subtract the eigenvalues, as soon as I subtract the eigenvalues from the main diagonal, a single Jordan block contributes 1 0 column to the null space. Okay? And when I take the power, when I take the square of the Jordan block, if its size is smaller, if its size is larger than 2, then larger than or equal to 2, then it's going to bring me an additional 0 column, which is going to increase the null space dimension. And if I take the power 3 of a 3 by 3 Jordan block, then I would get the 0 matrix, which is going to bring an additional 0 column, which would increase the null space dimension by 1. So each power increase in a single Jordan block would bring a single additional null space dimension. Okay? Until we reach the power 3, which is the size of the Jordan block. Okay? This is a 3 by 3 Jordan block. If I did this to a 2 by 2 Jordan block, then we would obtain the 0 matrix at the power 2. Okay? So, and this is the largest null space null space contribution we can get. The null space is going to increase its dimension by 1, and this is going to be the largest dimension we can reach. This is the largest number of 0 columns that we can reach. If I increase the power above the size of the Jordan block here, we see that there is no increase in the null space dimension anymore. Okay? So until we reach the power which is equal to the size of the Jordan block, the null space dimension grows by 1 at each increase of the power by 1. Okay? And once we reach the maximum power, which is the size of the Jordan block, then the dimension increase would stop for further powers. Okay? So this was the interesting idea that is going to enable us to be able to calculate these quantities here. Okay? So now let us go back to the 10 by 10 matrix. So in this case, what is D of S? Let us write what D of S is for this matrix. D of S in this case is, what is the size of the matrix? The size of the matrix is 10 by 10. So the powers in the D of S should sum to 10. So I would have S minus 2 as the first eigenvalue term and S minus 3 as the second eigenvalue term. All right? And now what about these powers? So here the eigenvalues are on the main diagonal. This is an upper triangular matrix. Eigenvalues are on the main diagonal. How many eigenvalues equal to 2? There are 7 eigenvalues which are equal to 2. And I have 3 eigenvalues which are equal to 3. This is my characteristic polynomial. So in this case, I have R1 is equal to 7 and R2 is equal to 3. Okay? These are the largest dimensions that we can reach for these individual null spaces. In this case, I don't know the minimal polynomial here, but I would like to determine it. M of S is going to be S minus 2 with a question mark here. I don't know the power. And S minus 3, I don't know the power. I will determine the power or the multiplicity by looking at the null space dimensions. When the power at which I reach the dimension 7 for the eigenvalue 2 for the corresponding null space, it's going to be the minimal polynomial power for the eigenvalue 1. And for the second eigenvalue, the power at which this null space reaches dimension 3 here is going to be the minimal polynomial power of the eigenvalue 3. So now let us try to look at these dimensions. So here, since the matrix is large, I won't be able to write what A-2 identity is. But let us first look at null space of A-2 identity. Now I want you to imagine yourself subtracting 2 from the diagonal elements of this matrix. Okay? Subtract 2, that is what A-2 identity means. Subtract 2 from the diagonals elements of this matrix. Okay? If you do that subtraction, you're going to see that I would get zeros everywhere here until here, and I would have 1, 1, 1 here. Okay? Now I want you to look at the non-zero diagonal parts here. When I subtract 2 identity, I would have 1, 0, 0 here, and then 1, 1, 0 here, and I would have 0, 0, 1 here. So you see that as soon as I subtract 2 identity from this matrix, these parts here, which are 1, 0, 0, 1, 1, 0, and 0, 0, 1, these columns would still remain linearly independent. Okay? So I see that as soon as I subtract 2 identity, I would get some zeros here, but these elements would remain non-zero. These elements correspond to the other eigenvalue, which is 3. Okay? And these elements would remain non-zero. And because these elements are non-zero, there is no zero column. There wouldn't be any zero column in these last 3 columns of the matrix. And these last 3 columns of the matrix would always remain linearly independent. The vectors 1, 0, 0, 1, 1, 0, and 0, 0, 1 are linearly independent. Therefore, these 10 element columns would always be linearly independent when we subtract 2 identity from this matrix, because these diagonals would remain non-zero, and that would make these 3 columns linearly independent all the time. So there wouldn't come any zero column here into this matrix, which would contribute to the null space dimension. So when I subtract 2 identity from this matrix, the parts of the matrix belonging to the other eigenvalue is 3, will not contribute to the null space dimension at all. So only the eigenvalues only the columns related to the eigenvalue 2 will contribute to the dimension of this null space. Okay? The columns belonging to the other eigenvalue or other eigenvalues will not be able to contribute to the null space at all. So let us try to write this dimension. What is the dimension of the null space of A-2 identity? This is the eigenspace for the eigenvalue 2, and I want to learn about its dimension. So now, as soon as I subtract 2 from these elements here, you see that I would get some zero columns. There would be a zero column here, because this 2 became 0. And these 2 rows, these 2 columns would still be linearly independent because of these 1, 0, and zeros, and 0, 1, zeros. So these 2 columns will not contribute to the null space at all, but there is a 0 column here which is going to contribute to the null space. An additional 0 column would always contribute to the null space. And as soon as so this is a 3 by 3 Jordan block, and as soon as I subtract 2 identity from it, I would get a 0 column, a completely 0 column, which is going to add into my null space dimension 1. Okay? And the other columns will not be affecting. So this Jordan block would be contributing 1 to the dimension of the null space, this null space. What about this 2 by 2 Jordan block? This 2 by 2 Jordan block, when I subtract 2 identity from it, is going to bring me 1 0 column here. And therefore this block will also contribute 1 to the null space dimension. And the other column will be 1 0 here. The other column will not be able to contribute. Okay? And what about these 1 by 1 2 Jordan blocks of size 1? So you see that as soon as I subtract 2 from this, I would get a 0 column here, and I would get a 0 column here. Okay? So these 1 by 1 Jordan blocks, each of them will contribute 1 to the null space dimension. And the rest of the non-zero columns would be linearly independent with each other. And that means that what is the dimension of this null space? When I subtract 2 identity from this matrix, each Jordan block will contribute 1 to the null space by adding a 0 column into the matrix. Okay? That means that here I would get the dimension which is equal to the number of Jordan blocks here. Okay? I have 4 Jordan blocks with different sizes, and each of them will bring me dimension 1 into this null space dimension. So this dimension is 4. Okay? Now let us try to imagine what happens when we take the square of this matrix. Null space of A minus 2 identity square. This is a block diagonal matrix, and when you square a block diagonal matrix, you just square its blocks. Okay? Remember, if you have a diagonal matrix, if you take the square of that matrix, then its diagonal elements would be squared. Okay? And when we have a block diagonal matrix, when you square that matrix, then its blocks are going to be squared. Okay? Let us see what is going to happen when I take the square. I subtracted already 2 from the main diagonal here, and these blocks would always remain, these parts will not again affect the null space dimension at all, because they are belonging to the other eigenvalue, and because they belong to the other eigenvalue, they won't affect the dimensions of null space of A minus 2 identity to a power. All right? Whatever you do, you take the square, you take cube, it really doesn't matter. These parts, as long as these diagonal elements remain non-zero, they won't be able to change the null space dimension at all. And these 3 columns belonging to the other eigenvalue will not affect really the null space dimension at all. Okay? And here let us see what is going to happen. When I subtract 2 from the main diagonal, and when I take the square of this block, I know that these 1s are going to travel into this corner. Okay? They are going to travel to this corner, and I would get 1 additional 0. Remember our investigation of this single Jordan block. These 1s are going to travel 1 diagonal up, and they will come here as a single 1. And you see that I would get an additional 0 column from there. Okay? And that means that this is going to add to this dimension 4 just 1 0 column, which is going to make this dimension 5 due to this block. What about this block? So this block is a 2 by 2 Jordan block, and when I take its square, when I subtract 2 from the diagonal, and when I take the square of this block, because the square power is equal to the size of this matrix is going to be completely 0. Subtract 2 from the diagonal of this matrix and take its square. You would see that this is going to be 0, 0, 0, 0. Okay? So in addition to this 0 column, it's going to contribute one more 0 column into the null space. So this contributed by 1 to the null space dimension by bringing an additional 0 column when I square it. And this is going to bring me one more 0 column when I take the square of it. And what about these 2? These 2 were already 0 at the first power. here at A-2 identity, these Jordan blocks were already equal to 0. They were completely equal to 0. So when I take their square, they would still remain 0, and they won't be able to provide any additional dimension to the null space. They won't be able to provide any additional 0 column to the matrix, okay? Because their size is 1. Their size is 1 by 1. Therefore, when I go to the power 2, they won't bring any additional null space dimension. Remember, when we take the power of a Jordan block above its size, when the power is above its size, then that Jordan block will not be able to contribute any null space dimension to us. So these two won't be able to increase the null space dimension at all, but these two Jordan blocks will bring us an additional null space dimension, which means that this null space dimension is going to be 6. And they're going to be contributed by these two blocks. Now let us look at dimension of null space of A-2 identity cube. And in this case, I know that at the second power these are 0. At the first power these are 0. Therefore, these three blocks, when I increase the power from 2 to 3, these three blocks will not be able to contribute to the null space at all. On the other hand, when I take the second power of this block, these ones came here. And there was a non-zero block, the non-zero column here. And when I take the cubic power of this block, I know that this block is going to turn into the 0 matrix. Even this 1 is going to disappear from there. Remember our investigation of this single block. At the cubic power, this 1 disappears and everything becomes 0 here. Okay? So only this block is going to be able to contribute an additional dimension to the null space when I increase the power there. Okay? So this is going to be 7. Okay? The dimension became 7 in this case. But 7 is the characteristic polynomial power for this eigenvalue too. Okay? So we reach the dimension 7 at the power 3. And according to this fact here, we are going to reach the dimension Ri at the power Mi. Since this dimension is Ri, this is going to be my Mi. So this power in the minimal polynomial of the eigenvalue 2 will be 3. Okay? So now, if I increase the power further, dimension of A-2 identity to the power 4, what would be this dimension? When we reach this dimension, nothing should change. Okay? When we go over Mi, nothing should change, and these should be 7 until infinity. Because all of these blocks turned into 0 blocks at the power 3. Then it really won't matter if I take the 4th power, 5th power, etc. These will remain 0, and all the columns related to the eigenvalue 2 would be equal to 0 for any further powers, any larger powers. And these parts will not be able to contribute at all when we look at A-2 identity. Okay? So this is how actually we can get the dimensions of these null spaces for a matrix in Jordan canonical form. Now let us go into the dimension of null space of A-3 identity. Okay? This is the other eigenvalue. This is the other matrix. A-3 identity. In that case, I will subtract 3 from the main diagonals of this matrix. Okay? Subtract 3 from the main diagonals, and I would get 0, 0, 0 here, which is fine. But I would get -1s for all of these columns. Okay? For all of these diagonal elements, I would get -1. And in that case, you can see that all of these columns belonging to the other eigenvalue 2 would be linearly independent. So these columns, when I look at the matrix, powers of the matrix A minus 3 identity, these 7 columns will not be able to change the null space dimension at all. I can take the square of this matrix. It really won't matter. As long as these diagonals remain at -1, these columns would always be linearly independent. The columns belonging to the other eigenvalue. So they won't affect the null space these null space dimensions here because they belong to the other eigenvalue. Only these columns would change this dimension. So as soon as I subtract 3 identity from this matrix, I would get 0, 0, 0 here, 1, 0, 0, and 0, 0, 0 here. So you see here that as soon as I subtract 3 from the diagonals, I would get 1, 0 column due to this Jordan block, 1, 0 column here, and 1, 0 column due to this Jordan block. Okay? So what about this dimension? This null space dimension is going to be equal to 2. Number of Jordan blocks belonging to the eigenvalue 3. Okay? The earlier one was 4 because there were 4 Jordan blocks for the eigenvalue 2. So we see that the dimension of the null space, dimension of the eigenspace is determined by the number of Jordan blocks belonging to that eigenvalue. Okay? And this is the number of linearly independent eigenvectors for the eigenvalue 3 as well. Okay? This dimension determines the maximum number of linearly independent eigenvectors because this is the eigenspace for the eigenvalue 3. All right? And now what is going to happen when I take the square of it? Dimension null space of A minus 3 identity square. In this case, I know that these blocks are irrelevant because they are belonging to the other eigenvalue. And this block was already, this 1 by 1 block was already 0 at the first power 1. So when I take its square, it's going to remain 0. So this block will not be able to affect the null space, increase the null space dimension at all. Because it contributed 1, 0 column at the first power. And since its size is 1 by 1, it won't be able to contribute any additional columns when I increase the power. Okay? But what about this? At the first power, this contributes to 1, 0 column into the null space. And when I take the square of that matrix, even this 1 is going to disappear from there. This is going to be the matrix 0, 0, 0, 0 when I take the square of that matrix. Just like this block in the second power. Okay? And in that case, this is going to be able to contribute. I had a non-zero column at the power 1 for this matrix. And even that non-zero column is going to disappear at the second power. That means that only this block is going to be able to contribute an additional 0 column to the null space, and that contribution is going to make this dimension 3. Okay? And you see that here, this dimension 3 is the characteristic polynomial power for the eigenvalue 3. Okay? So we reached the Ri, which is R2 here. We reached R2 at the power 2. We reached R2 equals to 3 dimension at the power 2. That means that this is going to be in the minimal polynomial. I need to have that power equal to 2. Okay? And what happens when I try to increase these powers any further here? 3 identity to the power 3 is going to be again 3, and this is going to continue forever. Okay? So now we have obtained these important results, and now I'm going to try to summarize these. Okay? So here we see that, for example, the dimension of this first null space, dimension of the eigenspace, actually gives us the number of Jordan blocks belonging to that eigenvalue. dimension of this null space here, for this one, I have 4 blocks, and this dimension gave me 4, which is the number of Jordan blocks belonging to the eigenvalue 2. And I see that this dimension is 2, and I had 2 Jordan blocks for the eigenvalue 3. Okay? So this dimension of this null space is really important. It is the eigenspace dimension, and it is giving us the number of Jordan blocks belonging to each eigenvalue. What about this increase here? This increase from 4 to 6. What does that number represent? So from 4 to 6, I add 2. What is 2 here about the number of Jordan blocks? Here 2 is the number of Jordan blocks whose size is larger than or equal to 2 for the eigenvalue 2. This increase from 4 to 6 happened because of these 2 blocks. And each of these 2 blocks has size larger than or equal to 2. Okay? Therefore, this increase gives us the number of Jordan blocks belonging to the eigenvalue 2 whose size is larger than or equal to 2. What about this increase from 6 to 7? We know that this increase happened because of this eigenvalue, because of this Jordan block. Okay? And this increase then represents the number of Jordan blocks belonging to the eigenvalue 2 with size larger than or equal to 3. Okay? The number of Jordan blocks which is larger than or equal to 3, whose size is larger than or equal to 3 is 1 for this one. That is why this increase happened. And what about this increase? It is not an increase from 7 to 7. So the increase is 0. What is that 0? It is the number of Jordan blocks whose size is larger than or equal to 4, which is 0 for this, belonging to the eigenvalue 2, which is 0 for this matrix. Okay? So here, for the second eigenvalue, this is the number of Jordan blocks belonging to the eigenvalue 3, 2 Jordan blocks. This increase from 2 to 3 happened because of this block. And therefore, any block whose size is larger than or equal to 2 is going to contribute to this increase, would contribute to this increase. Therefore, this increase, which is 1 from 2 to 3, happens because of the number of Jordan blocks whose size is larger than or equal to 2. And this increase, which is 0 from 3 to 3, happens because that the number of Jordan blocks whose size is larger than or equal to 3 is 0 for the eigenvalue 3. Okay? There are no Jordan blocks with size 3 or higher for the eigenvalue 3 for this matrix. Okay? So now let us try to write these findings. So here, the first finding, dimension of null space of A minus lambda I. So let me write sigma I here. Okay? Dimension of null space of sigma I. Sigma I is A minus lambda I identity. Okay? So this is going to be equal to the number of Jordan blocks for eigenvalue lambda I. Okay? 4 blocks for eigenvalue 2, 2 blocks, 2 Jordan blocks for eigenvalue 3. Okay? This is also at the same time number of Jordan blocks. JB denotes Jordan blocks with size larger than or equal to 1. Which size larger? All Jordan blocks have size larger than or equal to 1. Therefore here, this is just making the same statement, writing the same statement. Number of Jordan blocks with size larger than or equal to 1 for lambda I. Okay? This is at the same time the maximum number of linearly independent eigenvectors. okay, for each eigenvalue. This is the eigenspace. As a result, there are at most four linearly independent eigenvectors for the eigenvalue 2, and there are at most 2 linearly independent eigenvectors for the eigenvalue 3. This is at the same time maximum number of linearly independent eigenvectors for lambda I, okay, for the eigenvalue I. So this single number gives us this information. Now let me try to look at these differences. I know that these dimensions are going to increase for some power increases, and then they will remain the same, okay? So they are increasing and then they remain the same. They can of course stay with 2, and they can remain at 2. Sometimes this increase stops at the first power, okay? So here, then we are going to look at these increases. All right. So dimension of null space of sigma I square minus dimension of null space of sigma I. What is this difference representing? This is the number of Jordan blocks with size larger than or equal to 2 for lambda I. Okay? This 4 to 6 is 2, and I have 2 Jordan blocks for the eigenvalue 2 whose size is larger than or equal to 2. This has size 3, size 2. There are 2 Jordan blocks whose sizes are larger than or equal to 2 for the eigenvalue 2. And what about the next increase here? This is going to be dimension of null space of sigma I cube minus dimension of null space of sigma I square. Okay? And this difference is the number of Jordan blocks with size larger than or equal to 3 for lambda I. Okay? And this type of relationship continues until dimension of null space of sigma I cube, sigma I, let us say L, minus dimension of null space sigma I to the L minus 1 is the number of Jordan blocks with size larger than or equal to L for lambda I. Okay? So I want to write this in a better way. So I'm going to actually box it. Dimension of null space of sigma I to the L minus dimension of null space of sigma I to the L minus 1 is the number of Jordan blocks with size larger than or equal to L for lambda I. Okay? So we have got just this one. That's the main rule. And this main rule even works for L equals to 0. If L equals to 0, this becomes, if L is equal to 1. If L is equal to 1, dimension of null space of, let us say L equals to 1, then this becomes dimension of null space of sigma I to the 1 minus dimension of null space of sigma I to the power 0. Sigma I to the power 0 is the identity matrix. Okay? And what is the dimension of the null space of the identity matrix? Which vector is in the null space of the identity matrix? I want to solve this equation, Ix equals to 0, but we see that this makes x equals to 0. So only the x equals to 0 vector is inside the null space of the identity matrix. That means that this dimension is equal to 0. Okay? then this difference would be just dimension of null space of sigma I, which would be the number of Jordan blocks with size larger than or equal to 1 for lambda I, which is equal to the overall number of Jordan blocks. Because any Jordan block has size larger than or equal to 1. All right? So this fact holds even for L equals to 1, where this power is equal to 0. Okay? So now I will write just one more thing here. What can I say about these MIs? One was 3 and the other one was 2. Okay? What are these MIs? Why did this increase stopped at the power 3? This dimension increase stopped at power 3. When we go from 3 to 4, no dimension increase happened. Why was that? It was because of this block. The largest block became 0 at the power 3, which is MI. Okay? So I have M1 is equal to 3 and M2 is equal to 2 here, these powers. And this largest dimension was reached at 7 because this largest block happened to be exactly equal to 0 at the power 3. So no power increase was able to contribute to the null space dimension. Okay? And the largest Jordan block became equal to 0 at the power 3 because its size was equal to 3. And for the second eigenvalue, the increase stopped at power 2, which is M2, and increase stopped at power 2 because this largest Jordan block belonging to the eigenvalue 3 became 0, exactly 0 at the power 2. Okay? Why did it become 0 exactly at the power 2? Because its size was equal to 2. Okay? So what can I say about these M1 and M2? These M1 and M2 powers in the minimal polynomial, multiplicities in the minimal polynomial should be equal to the size of the largest Jordan block for each eigenvalue. Okay? Size of the largest Jordan block for the eigenvalue 2 is 3. Size of the largest Jordan block for the eigenvalue 3 is 2. That is why these minimal polynomial powers turned out to be 3 and 2. Okay? So here I can write an additional fact. And I can actually say here that MI is equal to the size of the largest Jordan block for lambda I. Okay? We have this fact about the minimal polynomial powers. So when you look at the Jordan canonical form of a matrix, you can directly say what it is minimal polynomial powers are. Just look at the size of the largest block for each eigenvalue. Then you will know those powers will be equal to them. Okay? So here, what is necessary for a matrix? So suppose that I am looking at a Jordan, I am trying to understand if the Jordan canonical form of a matrix is diagonal or not. Sometimes Jordan canonical form for diagonalizable matrices, Jordan canonical form turns out to be diagonal. Okay? In that case, what is necessary for the Jordan canonical form to be diagonal? Jordan canonical form should be composed of blocks like this, 1 by 1 blocks, 1 by 1 Jordan blocks. Okay? If all of the Jordan blocks has size 1 by 1, then the matrix, the Jordan canonical form of the matrix will be a diagonal matrix. Okay? So what is necessary according to this information? What is necessary about the minimal polynomial for the Jordan canonical form to be diagonal? I know that if the Jordan canonical form is diagonal, then the size of the largest block should be 1. There shouldn't be any 2 by 2 block because it is not diagonal anymore. Okay? The size of the largest Jordan blocks should be 1 for each eigenvalue for a diagonal Jordan canonical form. Okay? That means that a matrix is diagonalizable, which means that its Jordan canonical form is diagonal if and only if all minimal polynomial powers are equal to 1. Okay? So this is a very, very important fact. A matrix is diagonalizable if and only if all powers in the minimal polynomial of that matrix are 1. Okay? All multiplicities in the minimal polynomial are 1. So diagonalizability is fundamentally related to the minimal polynomial of the matrix, or more like powers in the minimal polynomial of the matrix. Remember the distinct eigenvalue case. In the distinct eigenvalue case, d of s is equal to m of s, and all of the multiplicities in the minimal polynomial and the characteristic polynomial are 1. That is why the distinct eigenvalue case is actually the case with a diagonalizable matrix. We know that matrices with distinct eigenvalues are diagonalizable, and that is because the minimal polynomial powers for those matrices are all equal to 1, which are the size of the largest Jordan blocks, which are 1, in which case Jordan canonical form turns out to be diagonal. Okay. So this is the fact about the Jordan canonical form, and now we are going to be looking at how we can learn about the Jordan canonical form of a matrix which is not in Jordan canonical form. Okay? Suppose that I am given a matrix A and I am wondering about its Jordan canonical form. What can I do? So I know that Jordan canonical form is P inverse AP. Okay? So now I'm going to subtract lambda I identity here. Okay? Lambda I identity and P inverse AP minus lambda I identity. Okay? We are going to see here that it doesn't matter. If I look at the null space dimension of A minus lambda I identity, then these are going to be the same dimensions as the null space of J minus lambda I identity. In the earlier example, we had the Jordan canonical form. Okay? So we learned how to calculate the null space dimensions of a matrix in Jordan canonical form. So we learned in the earlier example to calculate J minus lambda I identity. We learned how to calculate the dimension of null space of such matrices. But now we're going to make a connection between J minus lambda I identity null spaces and A minus lambda I identity null spaces. Okay? So I have J minus lambda I identity is equal to P inverse AP. Instead of this identity matrix, I will just write P inverse P. Okay? Because we know that P is an invertible matrix, and instead of identity matrix, I can write P inverse P. Okay? So now let me take P inverse parentheses on the right, like this. And P parentheses on the left, P inverse parentheses on the left and P parentheses on the right, okay? And inside I would have A minus lambda I identity, okay? So you see here that J minus lambda I identity is P inverse times A minus lambda I identity times P, okay? So now we have to remember some basic fact from linear algebra. Actually, I'm going to give the proof of this fact As an additional note, and I will upload it into the class. So fact is the following. Rank of a matrix does not change when it is multiplied with an invertible matrix. With an invertible matrix from the right or from the left. So the rank of a matrix does not change at all when we multiply that matrix from the right with an invertible matrix or from the left from an invertible matrix. P and P inverse are both invertible matrices. As a result, rank of this matrix, A minus lambda I identity, is always going to be equal to the rank of J minus lambda I identity. Okay? Rank of J minus lambda I identity is equal to rank of A minus lambda I identity. Because I have here a matrix multiplied from the left with an invertible matrix and then from the right with an invertible matrix. So these multiplications do not change rank. Therefore, the rank of this matrix inside is equal to the rank of the J minus lambda identity. Okay? So here, if rank, what is rank? Rank is dimension of the range space of J minus lambda identity. This is equal to dimension of the range space of A minus lambda identity. Okay? Rank is the dimension of the range space. All right? So now here, I'm just going to invoke the rank nullity theorem. If the dimension of the range spaces are equal for these two matrices, since the sizes of these two matrices are the same, the null space dimensions should be again the same. Okay? So dimension of the null space of J minus lambda identity is equal to the dimension of null space of A minus lambda identity. Okay? So we have this type of equality. So null space dimension of a matrix A minus lambda identity should always be equal to the null space of that matrix's Jordan canonical form minus lambda identity. Okay? We learned how to calculate this dimension. The earlier matrix was in the Jordan canonical form. We now know how to calculate this null space dimension. It is the number of Jordan blocks for the lambda I. Okay? But in reality, we don't have J. Okay? We only have A itself. So then if I can calculate this null space dimension, I would immediately know this null space dimension. And then if I calculate this dimension, I can calculate the number of Jordan blocks inside J. Okay? So you see that these null spaces do not change because of these P inverse P multiplications. What about the square of these matrices? Because we are not only interested in the dimension of this null space, we are interested in this matrix square, matrix cube. What about the dimension of their null spaces? It is really not difficult. Let me take the square of these both sides. J minus lambda I square is, I will multiply this multiplication with itself. I am taking the square of this. P inverse A minus lambda I identity, P, times itself. P inverse A minus lambda I identity, P. Okay? So you see that P and P inverse multiplication would give me identity, and this would be J minus lambda identity square is P inverse A minus lambda identity square P. So we see that the square of this Jordan canonical form minus lambda identity is A minus lambda identity square times an invertible matrix from the left times an invertible matrix from the right. As a result, dimension of the range spaces of these two matrices would be the same. Similarly, dimension of null space of these two matrices will be the same. So dimension of null space of J minus lambda I identity squared is equal to dimension of null space of A minus lambda I identity squared. Okay? You can actually continue with this logic for any higher powers. Okay? So you can say that dimension of null space of J minus lambda I identity to the power L is equal to the dimension of A minus lambda I identity to the power L. Okay? So in general, you don't have the Jordan canonical form. You want to find out the Jordan canonical form. But you can always calculate these null space dimensions. If you calculate these null space dimensions, you know the corresponding dimensions for the Jordan canonical form. And if you know these dimensions from these facts, you can understand the number of blocks in the Jordan canonical form, and you can try to find their sizes as well. Okay? So now it is what we are going to do in this last example. Sorry, it took a little bit longer than I expected, so I will stop after this example. So the example is not really difficult. So let us look at the example. A is given as follows: 1, minus 1, 1, 0, 1, minus 1, 0, 0, 0, 0, 0, 0, and 2, minus 2, minus 2, 0. Okay. So now I would like you to calculate the characteristic polynomial of such a matrix. This can be, for example, an exam question, and we might ask you what the characteristic polynomial is. Then you have to calculate determinant of Si minus A, which is D of S. And then you have to calculate Si minus A and the determinant of this matrix. I leave it to you as an exercise. So calculate and see that the characteristic polynomial of this matrix is S to the power 4. Okay? Now what are the eigenvalues? I know that the only eigenvalue is lambda 1 equals to 0 and R1 is equal to 4. Okay? The characteristic polynomial power of the eigenvalue is 4. Now I'm going to calculate the matrix sigma 1, which is A minus lambda 1 identity. And in this case, lambda 1 is 0. If it is not 0, you have to subtract lambda 1 from the diagonals. But in this case, lambda 1 is 0, so sigma 1 is A. Okay? So let me look at the dimension of null space of sigma 1. Okay? Dimension of null space of this matrix. So we see that here, how many linearly independent columns do we have? What is the number of linearly independent columns? We see that these two columns are the multiple of each other. If I multiply the first column with minus 1, I get the second column. Okay? As a result, there is only one linearly independent column among these two columns. So one linearly independent column, two linearly independent columns, and I have 0, so I have only two linearly independent columns, which means that the rank of the matrix sigma 1 or A is 2. Okay? So what about the null space dimension? It has 4 columns. By the rank nullity theorem, it should be equal to 2. Okay? So did we reach the largest dimension possible here? The largest possible dimension for this null space is 4. But the dimension here is 2. So I know that minimal polynomial of this matrix is not S minus, is not just S. Okay? minimal polynomial is not just S. The power at which I reach the dimension 4 will be the minimal polynomial power. Okay? Let us now look at sigma 1 square. Okay? Let us see if the dimension reaches 4 in that case. If I calculate the square of this matrix, I would obtain first 2 columns equal to 0, and then 1, 1, 0, 2, and then zeros here. Okay? So now what is the dimension of, maybe I should do it like this. I'm going to carry these dimensions to here. Dimension of null space of sigma 1 is 2. Dimension of null space of sigma 1 square is. The rank of this matrix is 1, only one linear independent column. Null space dimension is therefore 3. So I had it. Did we reach the largest dimension? Still not. The largest dimension should be 4. Still not. So the minimal polynomial is not S square. Okay? Because this can't be the minimal polynomial power. Then let us calculate sigma 1 cube. Now I'm going to, of course, there is nothing, there cannot be anything other than the dimension of sigma 1 cube is going to be 4. Now you know that from these results. Okay? So, but let us see here. So multiply this matrix with sigma 1 itself, which is A. Okay? And that is going to be 0, 4 by 4. Okay? So now what about the null space dimension? Null space of sigma 1 cube. Dimension of this should be 4 because rank is 0 and this is 4. Okay? So now we reach the largest possible dimension. That means that the minimal polynomial should be S cube. Okay? This should be M1. So now calculate the Jordan canonical form of this matrix. So this dimension is going to give me the number of Jordan blocks is equal to 2. Okay? It should be this dimension according to this result. Okay? And what about the difference? Number of Jordan blocks with size larger than or equal to 2 is this difference. 3 minus 2 is equal to 1. Okay? And I can look at this difference. Number of Jordan blocks with size larger than or equal to 3 is equal to this difference, which is 1. All right? And try to continue this logic, okay? So what would be the dimension of null space of sigma 1 to the 4? In that case, if you increase the power any further, it would remain at 4. There is nothing to grow, okay? The largest dimension will remain as 4. So what about the number of Jordan blocks with size larger than or equal to 4? Then it is this difference, okay? According to this result, it is this difference. So 4 minus 4 is 0. All right? So what do we see here? There are no blocks whose size is larger than or equal to 4. Okay? There are no blocks whose size is larger than or equal to 4. All right? So, but the number of Jordan blocks whose size is larger than or equal to 3 is 1. Okay? What does this tell you about the blocks? Number of blocks with size exactly equal to 3. The number of blocks whose size is larger than or equal to 3 is 1, and the number of Jordan blocks whose size is larger than or equal to 4 is 0. That means that there should be one Jordan block with size 3. Okay? Number of Jordan blocks with size equal to 3 is equal to 1. Okay? So this Jordan block is this one. So So, and this Jordan block should be the same one, okay? The number of Jordan blocks whose size is equal to 2, size is larger than or equal to 2 is 1, okay? That means that this is that Jordan block whose size is 3, okay? And the total number of Jordan blocks is 2. That means that what is the number of Jordan blocks with size equal to 3? With size equal to 2, this is equal to 0, and number of Jordan blocks with size equal to 1 should be 1. Okay? So the Jordan canonical form of this matrix should contain 2 Jordan blocks, and the size of the first Jordan block should be 3, and the size of the second Jordan block should be 1. So if I write the Jordan canonical form of this matrix, it is going to be composed of 2 Jordan blocks. The first one size is 3 by 3. The second one size should be 1 by 1. The only eigenvalue here is 0. Therefore, the 1 by 1 size Jordan block will be equal to 0. And what about the Jordan block with size 3 by 3? In that case, I will have the eigenvalues which are 0 here, and the size should be 3 by 3. One above the main diagonal, I should have 1s, and I would have 0s everywhere else. Okay? So this is, and I would have 0s here as well. Okay? So this is the Jordan canonical form of this matrix. Okay? And how did we get this Jordan canonical form? We calculate the dimensions of A minus lambda I identity, and then from those, because they should be equal with J minus lambda I identity null space dimensions, we have extracted the corresponding Jordan canonical form block sizes and their number. Okay? So we're going to solve more examples on this topic. Actually, I will solve 2 more examples, but they are going to be remaining into the next lecture. Thank you very much for watching again. Bye-bye.